Here we'll talk about basic arithmetic of vectors. I will introduce them as convenient notation for solutions, but they appear throughout linear algebra. So the vectors I will be writing this time vertically because they take less space, and operations again are easy to align and see what happens. So imagine we have two vectors of the same length, vector v and vector u, and then the sum, the addition of these two vectors, works this way. We just add these arrays of numbers component wise. Similarly, if we have a vector and a scalar, meaning just a number, we can scale up or down depending on the number the vector we have. So that is multiplication by scalar. And these two operations are the basic operations we can perform on vectors. In varying the numbers of the vectors, we can produce more vectors. So the general thing we could do with these two operations is to form a linear combination. Say we have vector u, we have vector v, we have vector w, something else. We can multiply them by some numbers, by some scalars, take the sum, and that will be another vector. For example, imagine three vectors. Each of them with having three coordinates. And we could take the linear combination of them with coefficients 1, -2, and 1, and compute the result. The result will be a vector of the same length, consisting of three coordinates, and each of the coordinates has to be computed according to the recipe. So the first coordinate comes from the first vector with coefficient 1. The second vector contributes its first coordinate with coefficient -2, and the third with coefficient 1 again. So the total will be 1 minus twice 4 plus 1 copy of 7. In the second coordinate, we just do the same. So the second coordinate, the first vector, comes with coefficient 1 of the second vector, which is this 5, with coefficient -2, and of the third vector with coefficient 1 again. And the same for the last coordinate. And now if we do the math, if we do the arithmetic, in each of the coordinates we will have 0. So the linear combination of the three vectors we have is 0, although not all coefficients are 0. And this is called a linear dependence between the vectors. Let's look at another example of the same vectors, a linear combination of. This time we'll have -1 for the first, -1 for the second, and +1 for the last. Let's see what happens. In the first coordinate we'll have -1, -4, +7. In the second we have -2, -5, +8. And in the last we have -3, -6, +9. So this time the totals are 2 for the first coordinate, 1 for the second, and 0 for the last. The linear combination with these coefficients of our three vectors is that vector. And these linear combinations of vectors appear naturally in already that little linear algebra we have, say, solving a linear system. I will write it in a generic form. A linear system of n unknowns consisting of m equations. What I can see it as a linear combination of columns of the matrix of the system. So if I take these first coefficients for x1 and group them together into a column vector, they all come with coefficient x1. And then the second vector will consist of the column of coefficients for x2 and all the way to xn, which will be the coefficient for the last column of my matrix. And the sum of them will be equal to the column built out of right-hand sides of the equation. So each of these columns will have the same length m, the number of equations we have. And I'm saying now that the equation we have is nothing but this vector equation, that the sum of columns of the matrix of our system is equal to the extended part of that extended matrix. And the coefficients are the solution components of a solution of the system. So using this, it just comes from computing what the sum of these columns is with the coefficients we have. It will be just the left-hand side. The coordinates of the sum will be just left-hand sides of our system. Putting it to practice, what we can say now is that these coefficients we used for the first linear combination computed form a solution of the system, of the homogeneous system with matrix built out of these three vectors. So what I'm doing now is I'm writing such a system that columns of its matrix will be just my columns. So for x in each of the equations, the solution will be the answers for x, y, and z. The coordinates, the coefficients for x in each of the equations I have will be coordinates of this vector. So 1 for the first equation, 2, these 2 for the second, and 3 for the third. And the same for y, just using the second vector, and for that using the last vector. So the second linear combination we computed can be now turned into a different statement that this bunch of coefficients we used, -1, -1, +1, form a solution of this time inhomogeneous system. So the equations start the same way as in here, but the right-hand sides are in the answer for the linear combination. Again, it's just computing this is the same as computing the linear combination of the columns we have, and the columns are again the coefficients columns of coefficients of a fixed variable. And just by design, the right-hand side will match the left-hand side. We could go with this analysis and even further and describe generic solution of this system without even solving it using Gauss elimination. We need to make one observation about the number of pivots in the system. The number of pivots a priori could be 3, but since we have a non-zero solution for the homogeneous system, it should be less than 3, because if it is 3, then there will be only one solution, and it will have to be the zero solution. Since we have a non-zero solution, the number of pivots will have to be less than 3, so it could be 2 or it could be 1. But if it is 1, then all the equations will have to be proportional to each other, which manifestly they are not. So that means that we must have 2 pivots. And since we have 2 pivots, we have one free variable, so we have one parameter family of solutions. And we already have one solution in this one parameter family, so all other solutions will be proportional to it. Generic solution will be scaling with some coefficient, which are now making a parameter t, of one of the solutions, and I can write it in a vector form like that. So that is the generic solution of the homogeneous case. Finding the general solution in this case is also possible. Again, we have 2 pivots. We already found it analyzing homogeneous equations, and then we have a solution of our non-homogeneous case. According to the general story of solutions, any other solution will be this known to us plus some solution of the homogeneous system, which we know in a generic form. So doing the computation, we will have -1 plus t, -1, -2t for the second, for y, and for that we have 1 plus t. That's a parametric description of, again, generic solution. It will be geometrically a line in both cases. Of course, we used some shortcuts which are only possible for systems of small number of variables. If we would have more variables, we won't be able to determine the number of pivots and hence the generic form of a solution. But usually we will deal with small systems, so these shortcuts are useful.